Anaerobic oxidation of methane. Anaerobic oxidation of methane (AOM) is a microbial process occurring in anoxic marine and freshwater sediments. During AOM, methane is oxidized with different terminal electron acceptors such as sulfate, nitrate, nitrite, and metals. Coupled to sulfate reduction. The overall reaction is CH4 plus SR42 HCO3 plus HS plus H2O. Sulfate-driven AOM is mediated by a syntrophic consortium of methanotrophic archaea and sulfate-reducing bacteria. They often form small aggregates or sometimes voluminous mats. The archaeal partner is abbreviated ANME, which stands for anaerobic methanotroph. ANMEs are very closely related to methanogenic archaea, and recent investigations suggest that AOM is an enzymatic reversal of methanogenesis. It is still poorly understood how the syntrophic partners interact and which intermediates are exchanged between the archaeal and bacterial cell. The research on AOM is hindered by the fact that the responsible organisms have not been isolated. This is because these organisms show very slow growth rates with a minimum doubling time of a few months. Countless isolation efforts have not been able to isolate one of the anaerobic methanotrophs. A possible explanation can be that the archaea and the SRB have an obligate syntrophic interaction and can therefore not be isolated individually. In benthic marine areas with strong methane releases from fossil reservoirs, e.g., at cold seeps, mud volcanoes, or gas hydrate deposits, AOM can be so high that chemosynthetic organisms like filamentous sulfur bacteria, sea vegeto or animals, clams, tube worms with symbiont sulfide oxidizing bacteria can thrive on the large. The bicarbonate HCO3 produced from AOM can get sequestered in the sediments by the precipitation of calcium carbonate or so-called methane-derived orthogenic carbonates, and Roman II get released to the overlying water column. Methane-derived orthogenic carbonates are known to be the most 13C depleted carbonates on Earth, with D13C values as low as -125 per mil PdB reported. Coupled to nitrate and nitrite reduction. The overall reactions are CH4 plus 4 and O3 C O2 plus 4 and O2 plus 2 H2O, 2O, 3 CH4 plus 8 and O2 plus 8 H plus 3 C O2 plus 4 and 2 plus 10 H2O. Recently, Anaerobic is shown to be responsible nitrate-driven AOM. The Anaerobic, named methanopredens nitroreducens, is able to perform nitrate-driven AOM without a partner organism via reverse methanogenesis, with nitrate as the terminal electron acceptor, using genes for nitrate reduction that have been laterally transferred from a bacterial donor. This was also the first complete reverse methanogenesis pathway including the MUCR and MER genes. In 2010, omics, especially metagenomics, analysis showed that nitrite reduction can be coupled to methane oxidation by a single bacterial species, Candidatus methylomirabilis oxyphorophyllum incetin, without the need for an archaeal partner. Environmental relevance. AOM is considered to be a very important process reducing the emission of the greenhouse gas methane from the ocean into the atmosphere. It is estimated that almost 80% of all the methane that arises from marine sediments is oxidized anaerobically by this process.